Welcome to the Pro Tips video series designed to arm biology learners with background knowledge needed to succeed during upcoming lessons. I'm Professor Workman, and this video continues our discussion of chemistry. We will consider a way of drawing valence electrons called Lewis dot diagrams that will allow us to visualize chemical reactions and bonding. A Lewis dot diagram is when you draw the electron configuration of an atom, then erase all shells except the important one for predicting chemical reactivity, which is the valence shell. This atom is lithium, or Li for short, and it has a single electron in its valence shell. So first I identify the element by its abbreviation, Li, and then I draw its valence shell and nothing else. Voila, that's it. Li with a dot on one side representing its single valence electron is the Lewis dot structure for lithium. Here is another example, oxygen. This is the total electron configuration for oxygen, in which you can see where all 8 electrons are located. So the Lewis dot diagram simplifies this by erasing shell 1. Voila! You are left with the valence shell only. Notably, the unpaired electron siblings can be drawn on any side. This is just a matter of artistic preference. So this second highlighted box is equally correct. It still shows 2 unpaired valence electrons that are looking for love and ready to react. For practice, I invite you to pause this video and use the periodic table to draw Lewis dot diagrams for these 8 atoms. Remember that the periodic table column, numbered here in light blue at the top, tells you how many valence electrons each atom has. Your diagrams should look like these. Let me point out a couple of noteworthy things. In beryllium, Be, the dots are drawn on separate sides. This one happens to be dots in the east and the west, but that's just artistic preference. You may have drawn them on any 2 sides, and that goes for all of these diagrams. Just make sure you didn't draw unpaired electrons together on the same side, because that would be wrong. Valence electrons are distributed in the 4 directions first, north, south, east, west, before they get doubled up. Any valence electron that remains unpaired is hungry for a partner and is highly reactive. Also of note, neon, Ne, has 8 electrons in its valence shell, and the valence shell is therefore full. This means that neon is not reactive. It does not participate in chemical reactions. Next, you can predict which of these atoms is likely to lose electrons during chemical reactions. Because of the low number of electrons in their valence shells, lithium, beryllium, and boron are likely to lose all of their valence electrons rather than try to pick up however many extra would be needed to fill shell 2. Once lost, the result is that shell 1 becomes their new valence shell, and it is full. Alternatively, you can also predict which of these atoms is likely to gain electrons during chemical reactions. The answer is nitrogen, oxygen, and fluorine, because they each need a low number of electrons to fill up shell 2 and therefore achieve the stability of a full valence shell. The only one of these diagrams we haven't mentioned so far is carbon. Carbon is an interesting atom because notice it has 4 unpaired and therefore highly reactive valence electrons. Thus, it can react with a variety of atoms and potentially bond to 4 different atoms at a time, which is a rare trait among elements. This makes carbon special. It can bring together atoms in all sorts of combinations, and this versatility is likely why living organisms are carbon-based. Now let's take it a step further and predict which of these atoms will partner up with each other. In these three examples, the goals of both atoms involved in the reaction are aligned. One wants very much to lose electrons, while the other is very happy to gain them. Nobody is protesting this exchange because they each achieve a full valence shell in the process. In these examples, there is an electron donor and an electron acceptor, and they match together. But sometimes atoms are in disagreement over who should control the disputed electrons. One such scenario is when an atom interacts with another of its kind. So consider molecular oxygen, or O2 for short. When an oxygen atom interacts with another of its kind, they both face the same challenge, that is, needing to gain 2 electrons to fill their valence shells. This creates a tug of war between equally matched competitors. Both are oxygen, so they have identical strength, an identical tug on the electrons. The result is that these electrons are shared exactly evenly. Neither atom is a donor or acceptor. Electrons involved in these bonds are as likely to be found near one atom as they are to be found near the other. And here's another way to draw bonded electrons. Each line represents a pair of shared electrons. So molecular oxygen has 2 pairs of electrons, and this is called a double bond. In summary, you learned that Lewis dot diagrams indicate valence electrons. You also learned that atoms react with each other if both can fill their valence shells in the process. You learned about electron donors and acceptors. Electron donors tend to lose electrons during reactions and bonding, whereas electron acceptors tend to gain electrons. Thanks for watching. If you liked this video, you might consider watching other videos in the series. Here's my contact information, and I always welcome any feedback. mworkman@pima.edu. Good luck in your biology journey.